And here we go. Hi, so my name is Quentin Oshem. Amongst other things, I'm leading the GNAT Pro product management team, GNAT Pro being our flagship product that includes in particular the compiler technology. And today, what I would like to talk to you about is this field called GPGPU and how we're planning to take advantage of this technology with the Ada programming language. But first, let's all align on what is this GPGPU thing. You might be familiar already, or probably are familiar already with the concept of GPU, which stands for Graphical Processing Unit. GPUs are found their way in the gaming industry a couple of decades ago, and they have been used historically to render real-time 3D scenes. And this is the kind of rendering that requires extremely fast, extremely efficient hardware to perform very specific and repetitive tasks. However, what happens is that we realize that the kind of things that GPU were good at could be extended beyond the bare graphical rendering application. Essentially, those architectures are good for anything that could otherwise be vectorized, think linear algebra. So in the recent years, they have been extended to a new field, which is called GPGPU for General Programming GPU. So the idea is to target a GPU and to run that piece of hardware, not only graphic rendering algorithms, but arbitrary program. How does that work in practice? Any GPU application is sort of a distributed application, if you will, where there are at least two pieces of distinct hardware. They can live in a single SoC, but there's nonetheless two different environments. On one end, you will have the traditional application that will run on the core, so maybe an ARM or x86 or PowerPC. So those core usually are general purpose. They are relatively big. They are very good at running complex sequential code, but you don't have so many of them. So for parallelism, it's not that good. In this example, I just have 9. You might have more, but it's still a relatively low number. On the other end, you have access to this GPU platform or GPGPU platform, which has in the order of magnitude of thousands cores, but every single of those cores is a lot more simple and a lot smaller, so it will only be good at performing certain operations. Those operations, by the way, are going to be accelerated maybe tenfold, maybe 100-fold, so the kind of speed up that you can gain by running a piece of your application on this GPU is often definitely worth the effort of taking the complexity of the distributed system that you develop. Now, this is one application that will go back and forth from the CPU to the GPU. The movement of the control flow from one end to the other is called the offload. And of course, that starts to raise all kinds of questions that you would not have if you were just programming that one CPU. To start with, how do we refactor the parallel algorithm? Let's say I have a piece of C code or maybe Ada code for what I personally care about. How do I identify the pieces that will be properly offloaded or offloadable, and how do I refactor the code so that I can rewrite the computation appropriately? Then how do I optimize data transfer? We'll see that optimization is really key here, and it's quite easy to think that you're going to optimize because you run something onto the GPU, but actually you get a resulting application that runs slower. One of the reasons for that might be that there is too much data transfer back and forth, and then that's the bottleneck of the processing, and that creates an overall computation time that turns out to be longer. So how do you optimize that? Then we're talking about a massively parallel system with thousands of cores. How do you debug such an application is a problem. How do you avoid issues that are typical to the GPU? If you go back to the CPU world, usually when you have parallelism, you tend to protect data by the means of using mutual exclusion, a mutex, for example. But calling a mutex, calling a log takes time. It's a system call. It's an expensive call. On the GPU, you don't want to do that because you don't want to spend the time taking and releasing mutex all over the place. So you tend to scale the computation into matrices, for example, and you want to make sure that there's no dependency between 2 bits of computation. How do you ensure that to avoid this so-called races? And there are a lot of questions related to occupancy optimization that are very specific to GPUs. I want to share 2 examples of this kind of optimization to give you a taste on how different that might be from the usual CPU world. Let's say that I want to spread a call to do something, so some operation, and there's another piece that's called do something else, and these things are going to be called under the control of if statements. And on my GPU side, I have what we call blocks or string processors, which are groups of GPU cores. And there are many architectures that are a bit like that. The one that might be the best documented is the NVIDIA hardware, which, at least on some of the recent ones, groups cores in pieces of 32 elements. They call that string processor. So you got 2 here. The issue is that within a string processor, within a block of cores, you can only run one operation at a time. You can run that operation on multiple data, but you still need to run that one single operation. It's the vectorization paradigm, if you will. So depending on how I spread this operation, I may or may not take full advantage of my GPU. For example, let's say that X goes from 1 to 4 and Y goes from 1 to 32, and I iterate over X and Y to schedule all the work. So I'm going to spread this computation many, many times with different value of X and Y. And here, quite naively, I would say, I start to iterate around X, and then I do the inner Y iteration, and I schedule the first 16 jobs, asking them to do something, and then the next 16 do something else, and then do something again, and then do something else again. So I have groups of 16 jobs that are scheduled, and in this naive allocation of my resources, my first block or my first streaming processor happens to have 16 tasks that are supposed to be do something and 16 other that are doing something else. Well, I've just said that a given streaming processor can only do one operation at a time. So what's going to happen here is that while half of them are doing something, the other half are waiting for the first half to be done prior to being able to work. I've lost, just like that, half of the potential speed up of my application. And of course, if I arrange things differently, like instead of scheduling jobs by chunk of 16, I schedule them by chunk of 32, then I'm going to do 32 of do something, and then 32 of do something else, and voila, I'm optimized the occupancy of my GPU, and I will get the maximum speed up. Another example relates to data, which is a bit similar, is that the memory may be private to an actual core. It could be shared by a block or streaming processor, or it could be global. And of course, the higher you go in this graph, the more expensive the data access, but the more data, the more memory you'll have access to. So you can see here that in order to optimize my computation, I have to do things that in the world of CPU, I don't really have to do anymore. I mean, compilers on CPU have been good to do all of this kind of allocation and data optimization automatically. It's not quite the case in the case of GPU. I have to ask myself questions that I don't used to ask. So just to give a few ideas on what it is, what does that mean to program a GPU. Now, let's get back to the talk of today and Ada and answer to the question, why are we even talking about Ada in the first place? I have a few elements of answers to that, and the first element of answer is actually an extract from a study that VDC ran earlier this year. In full disclosure, this is a study that Ada Core funded, because you need to have somebody to have an interest to study Ada, but we did not get involved in the result, and we did not get involved in the way those results are presented either. This is VDC undoing. And we were expecting to demonstrate that Ada was more cost-effective than C in terms of development, but we are astonished by the results of the study, and in particular here in the aerospace and defense industry, which is an industry that has been using Ada for many decades. They found, in particular when they look here at a project that would be on an ARM processor, they found that if you are using Ada, on average, your project is going to cost 38% less than if you were going to use C. Okay? So this is the one reason why it might make sense to consider Ada. Now, today, Ada is a language only supported on the CPU, so it would be interesting to get some of that goodness, if you will, onto the GPU as well. I'm not going to go into the details on how you manage to get these kind of figures with Ada. There's a lot of material out there on the web that explains why Ada helps with the cost of developing software. But if you have a specific question on this, then you can ask that in the Q&A session at the end of this WebEx. Now, there's another reason why we are particularly interested into GPGPU here at Ada Core. It's just because our historical market, which is aerospace, defense, and transportation, has algorithms today that could greatly benefit from GPGPU acceleration. And here are a few examples that we encountered on the field. Signal processing, I'm thinking of radar application in particular, machine learning that is finding its way in all sorts of things these days, simulation for Monte-Carlo, that's actually some banking applications that are using Ada that would benefit of it. Trajectory prediction, if you think of air traffic management systems, cryptography, which finds its way to all kinds of cybersecurity application, image processing, physical simulation, and so on and so forth. So not only would it make sense to use Ada for GPGPU, generally speaking, but our customers, our market, people using Ada today would also like to be able to better take advantage of GPGPUs. Now, on top of that, there is an interesting trend over the past few years, which is hardware availability. GPUs have been long on sort of server or desktop system, if you will, where you have relatively big and power-consuming system. In there, of course, you see NVIDIA as maybe the leader actor through either the GeForce for the gaming industry or Tesla and Quadro more for the server side of things. You will find the AMD Radeon, you'll find the Intel HD and maybe another Intel product right now. But even more interesting than that for us is the rise of the GPU availability on embedded system. And here, typically, you will have an SoC with a GPU running aside of a regular core. Again, NVIDIA here, which seems to be leading the story, has this Tegra platform, which you might know through the Jetson boards, where there is a GPU running aside of an ARM 64 chip that really allows you to do this kind of distributed application on an embedded board. They're not alone. ARM is also very well positioned on this market through the Mali GPU that you'll find on some of the ultra-scale boards. And then there are other players that we see less just because our market seems to be using them less, but they are around nonetheless. Hardware such as Qualcomm Adreno, PowerVR EMG, or Vivente from Freescale. So Ada seems to be a good fit. At least we'd like to be able to use it and to take advantage of it on GPUs. Our customers, our market, the Ada users have applications that fit, and you know what? They also have hardware availability today that could sustain the kind of embedded constraint they have. So it seems like everything is ready in our world to embrace GPU. So let's see what we can do. And as a word of disclaimer, today at Ada Core, we are on the way, we're on the path of GPU support. We have not selected exactly which technological answer is the best. This is one of the reasons why we organize these events, is to get the feedback from you guys so that you tell us, okay, this looks better than this. But we've been running studies, we've been running prototyping, we've been running experiments for the past 12 months, which allows us to present this picture today of what are the possibilities and where we are most likely to be looking at in the next 12 months. There's three big categories of solutions, I would say, available. One is just interfacing with existing libraries. One is integrating existing GPU language and porting them to Ada. And the third would be an Ada-specific solution that will use extensions of the Ada language as a means to support GPU programming. Now let's quickly go over the interfacing with existing libraries. By far, this is the less technical, exciting solution, but it has a tremendous advantage. It's already there today. There are a number of libraries out there that do provide GPU support for various kind of applications. If you, again, go from NVIDIA, you'll have all kind of linear algebra, optimized libraries available. You have libraries for image processing, OpenCV comes to mind. You would have libraries for machine learning, of course, through TensorFlow and so on and so forth. So all of these libraries usually provide C interface. It's perfectly possible to just bind those interface to Ada either manually or through some of the automatic binding generator, FDUP Ada spec being an option here, and then you would have access to the GPU to perform those very specific operations. We could even go one step further and imagine some of the Ada standard library, in particular Ada numerics, which has some metrics-related operations, to be directly bound to those things, so that from a developer perspective, he would use standard Ada that will be sort of magically accelerated when he writes the proper code. So, of course, the issue here is that you have to use a library that is pre-existent, or you might want to use a library that you would be developing in one of the languages available, but there's no Ada on the GPU per se. Ada is only on the host in this option, and the GPU is fully programmed by different technology. Now let's spend some more time on the, I would say, the more exciting part of this, which would be porting existing technology or existing languages, let's say, to Ada. And there's really three axes that we have in mind at this stage that are potential of interest. The first one is CUDA. So CUDA is the language from NVIDIA that allows to program GPU. It's kind of a C-like language, if you will. You would have a program that would contain both the GPU and the CPU code, and you would identify entry points to the GPU through so-called kernels. So the offload operation is essentially a specific call to a specific function with a specific convention that will go from CPU to GPU. There's a very, very strong advantage of CUDA over anything else being the NVIDIA language, which is the fact that it exposes all of the GPU capabilities that you might need to go as far as you can in terms of optimization. So if you're ready to select one hardware and NVIDIA looks good, that will give you a lot of room to go very far in terms of acceleration. Now, of course, the counter argument here is then you developing code that is extremely NVIDIA specific, and if you happen to want to consider other platforms, it will make your life a bit harder. For Ada, that could look like this, and this is actually code that we experimented with, so it's not fully slideware. We did run these kind of things in the lab. You would have a procedure, a function, which would have some array parameters most likely, which would be identified as a CUDA kernel, so an entry point. And here I'm saying that this function has one result, A, and two entry parameters, B and C. And then you would write that procedure, and the way it will work is that this procedure will be called in parallel several times on the GPU. So you need to be able to distinguish one call from the other. The way to distinguish that is to get some kind of an index. For example, the X index of the current thread, and every of these calls will have a different one at least if you wish so. So you can see here that I access to the index of the array through this get current thread element, and I'm saying that A at get current thread equals B at get current thread plus C at get current thread. Okay. It's quite straightforward here. On the host side, you would initialize those arrays, probably though some CUDA-specific setup, and at some point identify that specific call as being a call to a kernel, specifying some additional arguments, and here in particular I'm specifying how to map the kernel code onto the hardware with this notion of grids and blocks. So that's just the dimensions of my call and how to map onto this streaming processor I was mentioning earlier. And then I'm doing the call passing arguments. What's quite nice about CUDA here is that there's a lot that the compiler does for you, and you can share data representation between host and device, which will ease integration of those two pieces of code. Now, how could we support that? Well, it would be very easy again to provide APIs bindings to the CUDA APIs, and maybe that's not a very well-known fact, but we are working here at Ada Core into connecting our Ada frontend to the LLVM compiler, which happens to be the base of the CUDA compiler as well. So that's actually the experiment that we ran. We tried our Ada LLVM compiler and checked if we could generate PTX code through the CUDA interfaces for it. The answer was yes. So this is something that we could complete and productize. Another route is OpenCL, and at the very high level, you might refer to OpenCL as the portable CUDA. Almost all, at least all those that we looked at, GPU hardware vendors, they provide their OpenCL toolchain. Okay, so OpenCL seems like a nice place to start if we want to have some level of portability. In the case of OpenCL, you really have two distinct environments, two distinct languages, the host one and the OpenCL GPU one, and all the calls between the two have to be done manually. I mean, you could imagine some more clever compiler, but by default it's manual code. On the device side, it looks the same, and again, that's an Ada view of it. The syntax or the actual call names to access to the indices might be a bit different. Here I'm using the get global ID of 0 instead of getting the thread X position, but the concept is the exact same. There's nothing specific here. On the host code, it is a bit more tricky because you have to do all these calls manually, and I'm just showing here a very simplified version of the 200 lines of code that were required to call this kernel in our experiments, but you have to initialize the environment to build the program, you create a kernel, you create all the buffers on the GPU side, then you value them, then you call the kernel, you wait for the kernel to be over, and so on and so forth. All of these steps needs to be done also with the CUDA example, except that a number of those can be automatically generated, while in the context of OpenCL, you have access to the API, so you have to do a bit more manually. How could we support that? How did we experiment OpenCL support? Well, on the API front, on the host front, again, we can provide the bindings. That's easy. And on the GPU, on the device front, it's not quite convenient to go to every single one of these hardware vendor, every single one of these GPU vendor, and tell them, hey, you've got a GPU compiler. How about I connect my Ada compiler to your OpenCL compiler, right? That would be a significant amount of effort each and every time. There is an alternative to that through a technology that we offer today called CCG for common code generator. The way CCG works is that it takes a subset of the Ada language. If you know our technology, it's a bit similar to the zero footprint subset. So it's an embedded bare metal minimal subset of the language, and it translates that into C. It was initially developed to be able to offer in Ada solutions to people using targets we don't support today. It is not that difficult to adapt CCG to be generating OpenCL code instead of C code, and that would give a very nice and portable solution here. That's the second option. The third option that we have is OpenACC and OpenMP. Now, these things are a bit similar. They target kind of different hardware. OpenMP is more multiprocessor. OpenACC is more GPU, although it seems like nowadays those two are converging. And the idea is that you're going to parallelize loops, and you're going to identify the loop that needs to be parallelized by the means of a pragma. So it's extremely easy to integrate in the code. I mean, you might need to refactor it, but when it's refactor, you just put the pragma at the right locations. You don't have to create new function. I mean, you could as well, but you don't have to. There's only one language. That's the language you're developing with sections that are restricted to OpenACC or OpenMP constraints. One of the disadvantages that we've seen during our experiments is that as the technology stands today, in particular on GCC, there are some constraints, some limitations on the level of optimization. I mean, you have less direct access to the hardware, but that may be just transient limitations. And as you can see here, just in one slide to demonstrate the same example, I've got a loop that is looping here on the range of A. I'm saying this loop has to be parallel. That's a directive to the compiler, and I'm just doing the normal operation afterwards. And the compiler will know that this procedure has to be essentially compiled twice, if you will, once for the native code, the host code, and a second time to the target. And all these glue codes, all this memory copy and setting of the environment and so on and so forth will be done automatically. Of course, this is a very simple example, and that's the case for all of these things. Those three options, those three languages are actually much more complex and offer much more functionality to go much deeper in the various ways to optimize, but that just gives you the gist of how they work. So how would we support OpenACC? Well, there is a GCC implementation today that targets NVIDIA PTX, so all the NVIDIA hardware that we could adapt and connect to GNAT. And as a matter of fact, we did it and we checked that it works and that it could be done in a very small prototype that was developed in the past few months. So there are a lot of options for porting existing technologies, some that look more interesting from a user perspective than others, some that look more interesting from an acceleration perspective than others, or portability perspective. There's a bit of a trade-off between those things to be decided upon. One last option that we considered was to extend the Ada language itself. And here, this is very close to the idea of OpenACC. It could even be an Ada standardization of OpenACC or OpenMP-like standards, if you will. You can see here, that's the exact same example. The only difference is that instead of using a pragma, I'm using an Ada reserved word parallel. The advantage of modifying the Ada language is that we might be able to support more complex constructions and more advanced checking on the code. Now, this is a very early study. We don't know exactly how far that's going to go, but that, by all means, one of the options, one of the avenues that we are looking at. And this is not to say that amongst those that we're talking about, there's only one to be selected. It might be a combination of those things that will make sense at the end of the day. Just for the purpose of completeness, what we've shown here really is how to mark a piece of code as to be parallelized. There are a lot of other functionalities to consider, things such as how do I map the memory layout, like the OpenACC example I have didn't show that, but there is a way to do that as well. How do I allocate my threads on the hardware? How do I do this thing called reduction, where let's say you have thousands of results, but they should be all gathered into a buffer, or they should be all gathered into a number. If you think of how to compute p, for example, or pi, sorry, you would have a lot of intermediate results that you would combine with just a plus. Maybe you need containers, maybe you do need mutual exclusion in some cases, and you would try to avoid that as much as possible, but in some situations there is no choice, and you would need a sort of a GPU mutex for certain things, and so on and so forth. Okay. So those are the options that we are looking at today. Now, one word on Ada and formal proof. So the formalisms that we've studied, CUDA, OpenACC, OpenCL, they are really geared towards efficiency. They are geared towards acceleration, which is absolutely the #1 need that you have when you go to GPU. There's no reason to go to GPU if it's not to get 10 or 100-fold acceleration. Now, as programs are getting more and more complex, you find the usual software engineering requirements, and you might start thinking of how do I improve the safety, the reliability, the security of that piece of code that is running on the GPU. It used to be just a few lines of code. Now you can have entire program, sometimes that, let's say, entire sections of a program that run on the GPU that runs over hundreds or thousands of lines of code. So maybe there's something to do there. And it doesn't seem like the existing languages have put a lot of emphasis on this aspect, which may be just because they're coming from a sort of a C development perspective, which is historically not focused on safety and reliability. Debugging is hard. It's really hard. So if you have like thousands of lines of code that runs on all this core, and you have a bug on one specific execution, finding it, debugging it is difficult. If you can avoid those problems, it's all the best. So here, Ada and Spark by themselves, in their own right, without anything specific done to them, are already helping a lot. I mean, it is very easy in Spark, if you develop in the Spark language, which is a subset of Ada, to demonstrate formally complete absence of runtime errors. I can write a code in the Ada subset called Spark, run some proof, maybe make some modifications to make sure that the right information is at the right place or the right constraints are at the right place, and come out of that and say, this program has no exception. There's no buffer overflow, there's no range check failure, there's no division by zero, and so on and so forth. Okay, so this is already a very strong result. On top of that, there are some specific problems of GPU that could be formally proven with Spark. There are some properties that can be guaranteed. And the one that I want to highlight is the data dependency or race conditions that I was talking about earlier. I mean, in the general form, when you have a loop in an iterative code, often one loop depends on the iteration before. Of course, if you have n that depends on n minus 1, you cannot parallelize because you're going to run everything in parallel. There's no order. So, that's one thing that you want to verify, and if you can verify that formally, it is great. Another thing that you may want to verify are race conditions, where you want to make sure that two pieces of data are not written, or let's put it the other way around. One specific piece of data is not written by two separate threads. And you see in this very simple example, I mean, maybe it stands out to you already that there's a bug in there. It did not to me initially when I wrote this code, I have to confess, which is the reason why I'm talking about here. I've got an array that is indexed just one dimension, but really is a mapping of a two-dimensional array, x and y. I'm looping over x, I'm looping over y, and let's imagine that the content of this loop has to be spread over thousands of GPUs, and I'm computing the index of the array according to x and y expression. Okay, and for each index, I'm doing some computation. Well, of course, here, if I look at the math, there are a lot of situations where two different x and y would end up to be the same piece of data. Let's take x equal 100 and y equals 1. That gives me the index 110. X equals 10 and y equals 10 also gives me the index 110. So here there's a bug in my code, and there's an overlap in memory. This is, of course, a very obvious case. If you think of a larger piece of code where maybe those overlap only happen on corner cases, it would be very nice to have a tool that formally demonstrates that this does not happen. So we talked about why we would care about Ada and Spark on GPU for various reasons. We talked about the options that we studied up until today on how we would do that. And let's now quickly review the steps that we have here at Ada Core. So again, this overview is the result of about a year of studies and experiments on our end, out of which the survey that you actually already completed. So there's a survey after the webinar, but there was one before the webinar as well. So that survey was part of this study for us. And one thing that didn't stand out initially, is that it seems like OpenCL is the place to go, is the first or the most significant or useful implementation we can go towards to. Several reasons for that. It seems to be well used and largely adopted already. It is portable, and also in the data there is, let's say, a large chunk of users that are on NVIDIA hardware. There are also users on other hardware, and they will be difficult not to support those as well. And it's available across, in terms of portability, I'm talking about hardware, but it's also available on a number of OS solutions. I'm thinking of VxWorks in particular, which has a lot of penetration in our domain and has a better support for OpenCL at this stage. So this one makes a lot of sense. I must admit that personally, I got a lot more excited by the OpenACC or even Ada 2012 routes, because OpenCL makes me do more work. But at least for the next step, it seems like this is the most pragmatic avenue. So anyway, amongst the next 12 months, we are going to carry on experimenting and prototyping. So most probably largely going and studying the OpenCL route, hoping to have a prototype to share at some point. If you are interested, if you want to give us feedback, if you want to register to try the technology as a prototype when it's available, or if you have any interest whatsoever in GPU that you'd like to share with us and influence the direction of our development, by all means, please contact us on info@adacore.com, and we would be very happy to have a very open and candid discussion with you on those aspects. And here is the email address again. So that concludes the presentation part of this WebEx. I'm now going to go to the Q&A session, and I'm probably not going to answer to all the questions. Some might be relevant to the wide audience, some might be more targeted, but I'm going to try to do as much as I can. Okay, so I see some questions about connecting to the WebEx. I hope that those are solved. Let's see, I have one question on the Rust language. So Rust is not a language that we have large experience on today at Ada Core. We have a little. We looked at it to see how it would fit into the security story and the safety story for us. We got inspired by some of the Rust functionalities in the next standard of Ada 2020 or the new Spark, in particular the so-called pointer ownership. However, it would be difficult for me to say how does Ada and Rust compare on this specific issue of GPU programming. So I'd rather not go too far into the comparison here, just to give some insights on how we think of it and how we look at it. Are there any? Okay, I've got a question from around OpenCL. So will OpenCL option allow one to demonstrate absence of data overlap problem? The answer is absolutely yes. What the prover will have to know is how do you spread the data, the threads over the hardware. So then once you know that, if I go back to, let me go back to an example to illustrate that. Here you see that there's an X and a Y dimensionality here. So once you have this information, the fact that it's passed on a loop, or the fact that it would be a kernel is irrelevant. Spark just needs the information on the ranges, and it will be able to demonstrate that this expression here does not demonstrate distinct indexes with the ranges that are provided as input. So that's true for OpenCL, that's true for CUDA, and of course for OpenACC and OpenMP as well. All right, so I don't think there is any other questions, but by all means, if you want to have a discussion, and I know that some of you guys are coming from confidential environments, and it's not necessarily easy to share in a public forum like that. By all means, do contact us on info@telacore.com. We've had a number of discussions in the past few months that really helped us to refine our understanding and our positioning, and we would love to have some more to make sure that whatever we come up with is useful to the industry. And as I'm saying that, I'm seeing a comment from Howard that says that there are potential issues with some of the OpenCL implementation. So that's a very good comment, and that's something that we will definitely take into account. All right, well, thanks everyone for the attendance. And hopefully within another 12 months, we'll have another one of those, and we'll be able to present to you guys something more concrete that might be available for tryout. Have a good day or a good evening, depending on where you're calling from.